In this video, we're going to shift from Newton's laws and motion to energy. Energy is a scalar quantity that describes the state of a system. It can be converted from one form to another, but cannot be created or destroyed. Kinetic energy is a form of energy due to the motion of an object and is given by K equals 1/2 mv squared. As you can see, the higher the mass or velocity, the more the kinetic energy. Its unit is the joule, or J, which is kilogram meter squared per second squared, which is equivalent to a Newton meter. Let's talk about work, which is W. Work is the amount of energy transferred to or from an object due to a force acting on the object. If energy is transferred to the object, you get positive work. If energy is transferred from the object, you have negative work. So another way to look at it is that work is the change in kinetic energy on the object due to all the forces acting on it. The unit of work is also the joule, and it is also scalar. So work is basically applying a force over a distance. Any work is done only by a force in the direction of movement of an object. So if you have your axes and you have a force, and we call that phi, the angle between them, then the only work being done on the object is in the x direction, if that's the way the object is moving. That's the displacement. So work would be equal to force in the x direction times displacement, which is equal to F cosine phi times d. And it's often rewritten F d cosine phi. So no work is done perpendicular to the displacement. And this is also the equivalent of F dot d, the dot product. So to summarize, work is positive when the force is in the same direction as displacement. Work is negative when the force is in the opposite direction of displacement. And work is zero when the force is perpendicular to displacement. The net work is the sum of two or more forces acting on an object. And you can find net work one of two ways. One, you can find the work done by each force acting on the object and adding that work, or you can find the net force of all the forces and then use the formula F net d cosine phi to find your work. Now let's look at the work energy theorem. This theorem says that work is equal to the change in kinetic energy of an object, which is equal to the final kinetic energy minus initial kinetic energy, or 1/2 mv final squared minus 1/2 mv initial squared. We also can then say that the final kinetic energy is equal to the work done on an object plus its initial kinetic energy. So if its initial kinetic energy is 0 because it's at rest, then the final kinetic energy would be equal to the work done on it. Let's look at some specific cases of work. So first we can look at work done by gravity. Well, we call that W sub g, and that's equal to the force of gravity over a distance. And that will be equivalent to the mass times the gravity constant times displacement cosine phi. And let's call the work done by the applied force equal WA. So that's an applied force. Well, if the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy, then that would be equal to the work applied plus the work of gravity. And let's say you have an object that starts with an initial velocity of 0 and ends with an initial velocity of 0, or is constant, then final kinetic energy will equal initial kinetic energy, and the applied work is equal to the minus work done by gravity. In other words, gravity can often work against the applied work. And let's give an example. Let's say you have a person that's lifting a barbell, and it starts on the ground at rest, V equals 0, and he ends up lifting it over his head. Again, V final equals 0, and it moved a displacement d. Well, in this case, the V0, or the V final velocity, equals the initial velocity, which is 0. That means kinetic energy final equals kinetic energy initial, which is 0. So there was a force acting to raise the barbell, but no net work was done. And you might think that doesn't sound right, because you could be straining a lot to lift it, but in physics that's considered no work was done. And the reason is that the lifter applies an applied force, and which results in applied work of W, but that's equal to minus the work done by gravity. So there is work being done to raise the bar, but gravity is also doing a negative work against the bar, so we end up with the total work being 0. Let's try another example. You have someone who's throwing a ball up in the air. So the direction of motion is up, but the force of gravity is down. So we have the force being applied opposite the direction of motion, or in this case phi is 180 degrees. So the work of gravity is equal to a minus mg d, because the cosine of phi is a minus 1. So you throw the ball up in the air, and gravity does work to slow it down. Now the ball reaches its maximum height, and the ball is coming down. Okay, so that's the direction of displacement, and gravity again, force of gravity, is going down. So in this case, phi is equal to 0 degrees, and cosine of phi is equal to 1. So we get the work done by gravity is equal to a positive mgd. So gravity is helping to speed up the ball on the way down. And let's take another one. Let's look at work done during circular motion. So you have an object going around in a circle, and let's say this is the displacement, which is tangential, and you have centripetal force going into the center, and that's because the object is tethered to a string, and that string is going around the circle. So in this case, your centripetal force is actually perpendicular to the displacement. Displacement is going tangential, centrifugal force is going normal or perpendicular. So in this case, the work done is 0. But let's do the same thing with a force as the direction of displacement. And let's say you have a little movement dl, which is the little section of arc that passes between A and B, and you have your centripetal force. But let's say you have a force directed in another direction. Well, you do have work because you do get work in the direction of the motion, and in this case the work would be equal to F cosine phi dl, where phi is the angle between the motion and the force. Let's look at another type of work. In this case, we'll do work done by a spring. So if you have a spring attached to a block, this is your x-axis, and at rest, we'll call that x equals 0, and that's the relaxed state. So the spring is not moving at all. So the spring is relaxed at x equals 0. At this point, it can be compressed or it can be pulled. However, the spring will resist the motion in either direction. So the spring has a restoring force that tries to move it back to x equals 0. And again, that's in the opposite direction of the initial force. This restoring force is given by Hooke's law, and that states that the restoring force of a spring is minus k times the displacement, where k is equal to the spring constant. And the units for that are newtons over meters. The minus sign indicates that the spring force is always opposite the direction of the displacement d, trying to return it back to x equals 0. Now the spring does work, and we'll call that Ws, the work of the spring. But the force on the spring is not constant. In the previous examples, the force was constant, but for a spring, it's not. So we have to use calculus to define and find the work. In this case, the work done on a spring is equal to its final position, initial position, minus F dx. And we're assuming that the spring is going in the x direction only. So if you work through this integration, you get Ws is equal to 1/2 k x initial squared minus x final squared. You may wonder where the negative went to. Well, we ended up reversing these two to account for that negative. So this tells us that if that the work is positive if the final position is closer to the initial position of rest x0, and work is negative if the final position is further away from x0, and work is 0 if the spring returns to x0. And also from this equation, we can find that the work on the spring is equal to 1/2 k x final squared if the initial position was at 0. So to displace the spring, we apply a force, Fa. This force does work on the spring, Wa. So the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy, which is equal to the work done by the applied force plus the work done by the spring. So if the block starts and ends at the same position, then we have final kinetic energy equals initial kinetic energy, which equals 0, and we get the applied force is equal to a minus, the applied work is equal to a minus work done by the spring. Let's look at work done by a variable force. With a variable force, the equation W equals Fd cosine phi doesn't work. Instead, we'll have to use the integral of the force times distance. So what that looks like is that. And if the force is only in one direction, then we can use the integral of fx dx from x final to x initial. Lastly, let's look at power. Well, power is the rate at which work is being done. And we write that as power is equal to dw dt, and where w is the work. The unit of power is equal to a joule per second, and that's equal to a watt. And 1 horsepower is equal to 746 watts. So since we know what work is, we get power is equal to d dt, where this is work, which is equal to F cosine phi dx dt, which is equal to f v cosine phi. Or power is equal to f dot v, which is the dot product. Before we start doing problems, a couple of points. When doing work problems, always compare the direction of the displacement to the direction of the applied force. This determines the sign of the work. If force and displacement are in the same direction, work is positive. If force and displacement are in the opposite direction, work is negative. You may want to show the direction of the displacement on your free body diagram along with the force vectors. Also, don't confuse the direction or sign of a force with the sign of work. For example, gravity is a force that usually is downwards or in the negative y direction and is therefore negative. However, the work gravity does can be positive or negative depending on the direction of the displacement. Now for the first problem. A 120 kilogram bicyclist riding at 10 meters per second applies a braking force of 500 newtons over 10 meters in order to slow down. What is her final velocity after slowing? So we have a bicyclist moving in that direction, x, and she's applying a braking force, which is a force in this direction that slows her down. Her mass is 120 kilograms. Her initial velocity is equal to 10 meters per second. She applies a force of 500 newtons over 10 meters. So when we solve this problem, we'll use work is equal to force times displacement, which in this case is force times displacement times cosine phi, which is equal to 500 times 10 times cosine 180 degrees. And it's 180 degrees because the force is going in the opposite direction of the displacement. So that's equal to 5,000 times minus 1, or the work is equal to minus 5,000 joules. Now we want to find her velocity. Well, using the work energy theorem, work is equal to the change in kinetic energy, which is K final minus K initial. So we know minus 5,000 joules is equal to velocity final squared minus velocity initial squared. That's equal to 1/2 times 120 times v final squared, which is what we're looking for, minus 10 squared. That's equal to 60 times v final squared minus 6,000. Or if we solve for v final squared, that's equal to 16.7, or v final is equal to 4.1 meters per second. That's her speed when she slows. Let's do our next problem. A boy slides 8 meters down a 30-degree incline that has a coefficient of friction mu equal to 0.43. What is the work done by gravity? What is the work done by friction? What is the work done by the normal force? And what is the net work? Okay, so let's diagram this. We have our plane. This is 30 degrees. Okay. The boy slides down, displacement equal to 8 meters. We're going to call his height h. We know the friction, coefficient of friction is equal to 0.43, and his mass is equal to 20 kilograms. So for part A, we want to find the work done by gravity. Now, note that gravity is going in the negative direction, and the displacement is also going in the negative direction, minus y. So gravity is minus Fd, which in this case is minus mg times d. But our displacement is equal to minus h, again it's going in the negative y direction, which is equal to 8 sine 30 degrees with a minus sign. So that's equal to minus 8 times 0.5, or it's equal to minus 4 meters. So putting that in here, we get minus 20 times 9.81 times minus 4. So work done by gravity is equal to 785 joules. Now we want to know what the work done by friction is. Well, if we draw a free body diagram, we have our slope, we have the buoy, we have our normal force, we have gravity with a force equal to mg, and we have our 30-degree slope, and in this case we have y and x direction. So work of force is equal to negative F, the force of friction, times displacement. When solving problems with friction, we always want to solve for the normal force first. So we know Fn minus mg cosine 30 degrees equals 0. That's because in the y direction there is no movement, so the combined forces have to equal 0. So that gives us Fn equals mg cosine 30 degrees, and if we substitute in the values, we get 20 times 9.81 times 0.87, or normal force is equal to 170.7 newtons. Now we can find the work done by friction, which is equal to minus Fd, which is minus coefficient of friction times the normal force times d, and we know these values. It's equal to minus 0.43 times 170.7 times 8, which comes to minus 587 joules. And it's a minus sign because the buoy is going down the ramp while the force of friction is working up in the opposite direction. Now for part C, we want to know what the work is done by the normal force. Well, if you go back to our free body diagram, we have the buoy sliding down the hill. The normal force is perpendicular. So if we just look at work by the normal force is equal to F times D, that would be F D cosine 90 degrees. Well, the buoy is not moving in the direction of normal force, or even the opposite direction. It moves 0 in the y direction, so that's 0. And the cosine 90 is 0, so the normal force is 0. We could have known this just by looking at the free body diagram, because the normal force is 90 degrees to the direction of motion, and we know then that no work is done in that situation. For D, what is our net work? Well, the simplest way to do it is to add the work of gravity plus the work of friction plus the work of the normal force, which we found above to be 785, minus 587 plus 0, which comes to 198 joules. That's the net work of all the forces on the boy as he slides. Let's do our next problem that involves a spring. A block of 50 kilograms is 0.6 meters away from a spring and is sliding towards it on a horizontal surface at 3 meters per second. It hits the spring and is stopped momentarily by it. The spring has a spring constant K equals 20 kilonewtons per meter and is at its relaxed position. When the spring has stopped the block, it has compressed by 0.12 meters. What is the work done by the spring as it stops the block? What is the work done by friction? What is the coefficient of friction between the block and the surface? What is the velocity of the block as it passes through its original position after the spring rebounds it? Okay, so I drew the diagram, and you can see here's the block moving on a surface towards the spring in a relaxed state. It compresses the spring by 0.12 meters. For part A, we want to know what the work of the spring is, so we know that's equal to K initial minus K final, and that's reversed because the work of the spring is always negative to the direction of displacement. So that would be equal to 1/2 mass times V initial squared minus 1/2 mass times V final squared. Well, V final is 0 because the block momentarily comes to rest, so that's 0. So that becomes 1/2 mV initial squared. And if we plug those in, we get and this comes to 144 joules. So the work of the spring is 144 joules. For the next part, we want to know what the work of friction is. Well, let's review what's going on. We have the block moving in a plus x direction. We have friction moving in a minus x direction, and we have the spring pushing in a minus x direction. So this will cause a minus work for friction and a minus work for the spring, both of which act to slow the block. So using the work energy theorem, we know that kinetic energy final minus kinetic energy initial is equal to sum of the work, which is minus spring and minus the work of friction. Since the final velocity was 0, that becomes 0, and we get minus Ki is equal to minus Ws minus Wf. And if we reverse the signs, Ki is equal to Ws plus Wf. And if we solve for the work done by friction, we get initial kinetic energy minus work done by the spring. And that is equal to 1/2 mv squared initial minus 144, which we found up here. This is 1/2 50 times 3 squared minus 144. And if you work that out, the work of friction is equal to 81 joules. For part C, we want to know what is the coefficient of friction between the block and the surface. So, we just found the work done by friction, and that's equal to the force of friction over a distance, which is equal to the coefficient of friction times the normal force times the distance, which is equal to coefficient of friction times mg times the distance. And if we then solve for mu, we get mu is equal to the work done by friction divided by mgd. which is equal to 81, which we found above, over the mass times gravity times the distance. Now the distance that the block travels is a sum of the 0.6 meters till it hits the spring and another 0.12 meters till it stops moving. So the total distance is 0.72 meters. So if we put that in here, 0.72, that gives us our answer. The coefficient of friction, if you work this out, is 81 over 353, or it's equal to 0.23. That's our coefficient of friction. Now for part D, we want to find the velocity of the block as the spring pushes it back through its original point. So we have the block moving in to compress the spring. The spring pushes it back. So this was the original point, and we'll call the velocity there v1, and the distance it moved was 0.72 meters. And v initial is equal to 0 because it was at rest. So we know that kinetic energy final minus kinetic energy initial is equal to the work of the spring minus the work of the friction. Now let's take a look at the direction of these forces. The block is now moving in this direction. We have the force of the spring moving with the block. That's why its work is positive. We have friction moving against the block. Friction always works against the direction of movement. That's why its value is negative. So initial velocity was 0, so that goes to 0. So we get kinetic energy final is equal to, now we found these values above, 144 and 81. So 1/2 m v1 squared is equal to 144 minus 81, or 1/2 50 times v1 squared is equal to 63. V squared is equal to 2.52, or v1 is equal to 1.59, the velocity of the block as it returns to its original position. Let's do a problem that's a little bit more straightforward. A force F equals 2I plus 6J newtons causes the displacement of D equal to 3I minus 8J meters. What is the work done? Well, for this, we could use work is F dot D, which is the dot product. So let's review the dot product of vectors. If you have two vectors, A dot B, that would be equal to AX times BX plus AY times BY plus AZ times BZ. And you would get a total amount because this is a scalar, and you would just add all the values you found for each component. So going back to the original problem, we have work is equal to AX times BX, which would be 2 times 3, plus AY times BY, which would be 6 times a minus 8, which is equal to 6 plus a minus 48, or the work done is equal to minus 42 joules. Our next problem is a force F equals xi plus y squared j moves a crate in a straight line from x equals 2 meters, y equals 3 meters, to x equals 4 meters, y equals 6 meters. What is the work done? Well, in this case, we can't use work equals force times displacement because the force is variable. So we're going to have to integrate. And the formula for work using integration is F equals the integral of fx dx plus the integral of fy dy from point 1 to point 2. So in this case, fx is equal to x and fy is equal to y squared. So we get work is equal to the integral of x dx, and x goes from 2 to 4 plus the integral of y squared dy, where y goes from 3 to 6. And if you do the integration, we get that's equal to 1/2 x squared from 2 to 4 plus 1/3 y cubed from 3 to 6, which becomes 1/2 times 16 minus 4 plus 1/3 times 216 minus 27, which if you carry this through is equal to 69 joules. Let's do a couple problems about power. The first one is the work being done by a machine is given by work equals 72 times the square root of t joules. What is the power at 9 seconds? What is the average power from 0 to 9 seconds? So the first thing is we want to know what the power is specifically at 9 seconds. So power is equal to dw dt. We know that work is equal to 72 times the square root of t over dt, which is equal to 72 times t to the minus 1/2, which comes out to be 36 over the square root of t. And at 9 seconds, that's equal to 36 over the square root of 9, which is 36 over 3, or power is equal to 12 watts. Next part is it wants to know what the average power is from 0 to 9 seconds. Well, the average power is equal to the total work done over the total time, which in this case is 72 times the square root of t over the total time of 0 to 9 seconds, which is 9. And we then get the average power, because the time is 9 seconds, is 72 times the square root of 9 over 9, which is equal to 72 times 3 over 9, or the average power is equal to 24 watts. Let's do our last problem. A force is exerted on a box of F equals 8I minus 2J. This causes the box to have an average velocity of V equals 6I minus 1J. What is the average power? So our force is equal to 8I minus 2J, and we have an average velocity equal to 6I minus 1J. So power is equal to force dot velocity. So we need to do the dot product as we did in a previous problem. So we get power is equal to 8 times 6 plus minus 2 times a minus 1, which is equal to 48 plus 2, which is equal to 50 watts. So our answer is 50 watts.